Okay, I'm back, and I just wanted to go back to the Cepheid variable stars and mention that this particular technique is going to be useful for measuring the distance out to 10 to the 8th light years. Now, our galaxy is 10 to the 5th light years. So no, I'm putting a line here to indicate that these techniques would be good for finding stars in our galaxy, but this technique would be useful for finding other galaxies, the distance to nearby galaxies. You could use this technique in order to do it. I also wanted to mention that this method is not useful for distances greater than 10 to the 8th light years, because a Cepheid variable would then just be too faint to notice that it is oscillating back and forth. All right, so now we were going to go out and talk about the Tully-Fisher relationship. So now we're not looking at stars anymore, we're looking at entire galaxies. And in particular, we're looking at how fast is the galaxy rotating. We're going to measure the speed of the rotation of that galaxy. So we're going to measure the distances to nearby galaxies using this technique. So now we know the distance r to nearby galaxies. Okay, and then we're going to also measure their apparent brightnesses using the photometer. So now we've got the F. Okay, and now we're going to measure their luminosities using photometry. So F is equal to L divided by 4 pi r squared. So now we've got the luminosities of these galaxies that are close to the Earth. Okay, now we're going to measure for each of those galaxies how fast is it rotating by using the Doppler effect. So that if you've got a galaxy that is rotating like this, and let's say that the Earth is down here, then that means light on this side over here is moving away from the Earth, but light on this side of the galaxy is moving towards the Earth. So that means that we could take our diffraction grating, and the light is going to pass through the diffraction grating, and we're going to notice that if a particular color normally plots there on our black body spectrum, if that light is moving away from us, it's going to be shifted over to here. So it's going to be red shifted. And if the light is coming towards us, it's going to be blue shifted, and it's going to be over here. Well, depending on how far the light has shifted, we can use the Doppler effect to figure out the speed of the rotation of the galaxy. It can be done. So we're not going to do it. I'm just telling you that we can actually measure how fast a galaxy is rotating. So now we know the brightnesses of these galaxies, and we also know how fast they're spinning. So we plot it. So on a piece of paper, we're going to plot the brightness of these galaxies versus how fast are they rotating. And we get that bottom graph there. All right, so now we're going to be interested in a star or a galaxy that's even further away. So a galaxy that is further away than this number here. All we've got to do is, using the Doppler effect, we're going to measure how fast is it rotating. Okay, then we're going to go to this chart here, and we're going to find the rotation rate on the bottom, bounce it off the curve, and then that's going to tell us the real brightness of that galaxy. We can measure the apparent brightness of the galaxy with the photometer. So now we've got this one and we got this one, and we can use the photometry equation to get R and now we know how far away this unknown galaxy is. And you can see that this technique is good out to 1 billion light years away from Earth. We can measure distances now out to 1 billion light years by using this technique. However, and so here is a worked out example of how you would use the formula in order to do it. Okay, this method is not useful for distances greater than 1 billion light years because the galaxy would be too faint to measure its rotation rate. So there you go. All right, so now we are going to go out to even further distances by using supernovas. So I'll see you in just a moment.